Okay. Okay, now, everybody. So tonight, I mean today, we will um, get into the first chapter, and this is on the chi-square test and uh, non-parametric Kolmogorov-Smirnov test for equality of distribution. Okay, so and as mentioned earlier, I will add some more R elements into the assignment. So here is you can see I require that you use the R code and the example to use a chi-square test to double check your results. And then lastly, this is using a material from other resources. Excuse me. You can download it from here. Then follow the pages from 2 to 10. But I require that you generate excuse me, generate a random number from exponential function with mean equal to 1, and then follow the example, which I will show you and go over it in a little bit, to test if the sample are drawn from a distribution following a standard normal distribution. Okay, then use a Kolmogorov-Smirnov test to show why or why not. Okay, so there are 1, 2, 3, 4, 5 questions here. Okay, let me give an overview of the things that we are going over today. I mean, in this course. Okay, so for this 533 Z1 semester quarter, we will cover more advanced materials, and of course continuing to use the same textbook we used in the last quarter. Only the material will go more challenging and more advanced. Okay. The first module will cover goodness of fit test applications. Then in the second module, we'll talk about linear regression model, which is easy, but we will see. We'll have the multiple regression application. Okay. Then the third module will be on design of experiments. The fourth module on ANOVA table. ANOVA table is very much used in almost all the advanced statistical tests. It's the comparison of variance for the determining whether the multiple means are equal or not. Okay, then we want to see Bayesian estimation inference. Okay. And then non-parametric tests, and lastly, empirical method. Empirical method, we have 2 sections. We talked about jackknife method and bootstrap method. Okay, so this is an overview of the statistical method we will go over now in this 8 weeks. So firstly, let's look at the module 1 goodness of fit test application. We will only cover 7.1, 2, and 3. Okay, only 3 sections, and I will let me see, I'm opening it up right now. Okay, Yeah, the three sections that we are covering. The first is introduction. I'll leave that to your study. And I'll focus on the 7.2 and 0.3 sections on the chi-square test for count data. And then goodness of fit test to identify probability distributions. Chi-square test, sometimes we will have count data instead of the continuous data. So in this case, we usually use chi-square test to see whether the two is from a given distribution or they are independently distributed in that way. Okay, so you can refer to this example. It says values of some sort of subject of interest, and measurement could represent the count. For example, amount of carbon dioxide, CO2 in the atmosphere. There are many area of applications and so forth. Average monthly unemployment rate in the United States, hourly wind forces of a hurricane, etc. And in order to understand the behavior of these phenomena, then we need to identify the probability distribution that follows or given data are drawn from. For example, at a certain time, we may say that these data follow or come from normal exponential distribution. So it's no longer just a test for the equality of means, but the whole distribution. So in this case, we don't have compare just the center, but we compare the entire distribution. So how that can be done? We compare many points. For example, in the Kolmogorov-Smirnov test, we compare the different points from a distribution and then calculate the d-value. So based on that d-value, we will be able to determine whether the two distributions are identical or not. If the d-value is big, which is the absolute value of the differences, then that shows they deviate from each other significantly. However, if the d-value of the differences are small, then that shows that the two distributions are identically distributed. So therefore, you should not say that they are from two different distributions. So this should make sense as we see the graph in a little bit. Okay, so this is basically what we will cover here. Okay, now what I will do is I will use the example, okay, and in this textbook, and also another file that I will use to cover the method. Okay, so now we come to see the chi-square test for count data. Count data, they are usually, positive integer numbers, and this is the formula that we use to calculate it. Now, there's a q square here, basically approximately follows a chi-square distribution, and that chi-square distribution has k-1 degree of freedom. Okay, chi-square parameter for chi-square is k, and chi-square is the sum of k. K is the degree of freedom, so it's a sum of k, sum of the squares of k standard normal distributions. So chi-square is actually has the underlying assumption of normal distribution. Okay, now how do we do this? So if we look at this formula, we shall see up in the numerator, we are comparing the differences between and empirical value xi with with the theoretical or expected value from a given distribution, where pi, where here is the distribution here, and that distribution is a excuse me, that distribution is a multinomial distribution from with parameters n and p1 to pk, which means if you multiply n by p1, p2, p3 to pk respectively, then you will get expected values, count data again, similar, but in this case may not be integer. It can have decimal places, but that doesn't affect the result. Doesn't matter. Okay, so the point is that we compare empirical data, xi and xi. You have x1 to k, and then you compare that with this 1 to k ni. So these two group of paired values. All right. So then but then the differences, the negative sign might cancel out with each other. So you square it and take the sum and divide that by ni to get the ratio. All right. So and then obviously from here you can see that if the bigger, and then take the sum of them. So q square will always be positive, and so the bigger this value add up, the more different they are. Okay, so if the closer they are to each other, if all these values are identical to each other respectively, p1 n1, this value p1 n is equal to x1, and p2 n is close to x2, so on and so forth respectively, then what? Then it's q square will be very small. All right, this is the rationale. Okay, and here is a few conditions. Okay, conditions that we should have MPI greater than or equal to 5, and so forth. This is so that generally work well if we only have few values. So this need to be satisfied. Okay. Okay. We should. All right. We should know that the chi-square test we are studying in this section is an approximate test, valid for large samples. Okay. So it's called the observed frequency and denoted by OI. So O stands for observed, and MPI is called expected frequency denoted by E. So this formula is then equivalent to this to be more general or more identifiable. Okay. So, and this is called the goodness of fit test. In other words, you are not just, as explained previously, you are not just comparing the means. Okay, you are comparing multiple points, multiple values, and they are in pairs. Okay, and then calculate the sum of all these squares only in ratios, and that the sum of the ratio of these squares follows a q chi-square distribution approximately, and that's the rationale that we use here to conduct the test. Okay, I mean goodness of fit test. All right, and there are two categories. For example, a plant geneticist grows 200 progeny from a cross that is hypothesized to result in 3-to-1 phenotypic ratio of red flower to white flower plants. Suppose the cross produces 170 red to 30 white flowered plants. calculate Q square for this experiment. Do this data support 3-to-1 ratio? Okay, so from that question, we can compare it. Okay, to see what if we can identify the N, P1, P2, and then the what, X1, X2, which is in here 01, 02. All right, so we can see that 200 progeny. Okay, and then in which we have red, we have and white flower, each respectively, 2 kinds of flower, and we observe 170 as red, 30 as 30 as white. Then here's a hypothesis. Okay, the ratio. Okay, obviously if you just divide compare the ratio, that may be 5 or even 5.6 or 5.7 to 1. Okay, is that close to 3-to-1 ratio? May or may not be true. We don't know. I have to do a test. All right. And so given the 3-to-1 ratio, then we have the P1 equal to 3 plus 1, 3 over 3 plus 1 is 3/4, and then P2 is 1/4. Okay, and this obviously the conditions are satisfied. Okay. Okay, this condition is in a sense they are because as I mentioned, there are the underlying assumption for chi-square is that they are from normal distributions. So, and this is to make sure that it's not too skewed. The data is not very skewed. You don't have a very small p-value. If that's the case, if p1 is very small, then p2 should be very, very big. In that case, the test won't be reliable. Okay, so with that, then we can calculate expected value E1 and E2. Because given those ratio, if they follow that ratio out of 200, there should be 150 red flowers and then 50 white flowers. So with that, and then but actually you have 170 red flower and 30 yellow flower. So let's compare them respectively according to the formula. And this is how you calculate it, and you get the chi-Q square is 10.667. Now, so there's first part. Now the second part is that, will that be large enough for us to say no, reject the null hypothesis, which to reject that they are the same, because 170 to 30 is kind of too big odd ratio, so we don't say that they are equal to the 3-to-1 ratio. Okay, and here, given that alpha equal to 0.05, and so with that rejection region is 3.841. Here is, let me see. Here, the 1 means degree of freedom underneath in the subscript. And 0.01 is right tail, because this is, although looks like a 2-tail test, right? It is different or not different from, but in fact it's a 1-tail test, because we need to test. We need to say no if the Q square is greater. If Q square is small, and then we won't be able to reject the null hypothesis. So although the hypothesis looks like a 2-tail test, it's actually a right tail test. Okay, and if you plug in that into the table or in using StatDisk or using R, I prefer a simple tool like you know, chi-square. You can plug it in 1, 0.05. If you have download that analysis, probability distribution, chi-square, and you plug in degree of freedom is 1 to the right of the chi-square 0.05. You can see the chi-square value is 3.84. Okay, that is the critical value. Okay, or you can use Excel to easily calculate that. All right, so so that is the chi-square test of goodness of fit test using chi-square test. All right. Now here we extend to multinomial distribution. And so if you understand previous one, then this one shall be the same. The previous one is only 2. The 2 is kind of binomial, but here we have more. So look for this one example. Here we have before or after a TV station broadcasts a series of programs of ill effect of smoking marijuana. After the series, the station wants to know whether people have changed their opinion about legalizing marijuana, giving in the following tables database was surveyed. 500 chosen individuals. So, they want to change people's mind with the TV broadcast. See if they could reject. Okay, reject the you know, there's something evil about marijuana, and then people will change their mind. All right, so if there's no change of mind, then the distribution will be similar. If there's a change of mind, the distribution will be significantly different. So here we go. The first distribution is like that. And the second distribution is empirical distribution is like this. So we want to see if they are significantly different. So here again, we multiply all these values by 500, and then you can get the E1, 2, 3, 4. And then that by 500, you get 1, 2, 3, 4 also. And then find the difference, divide plug those in all formula, you get a very large Q square. And upon seeing that large Q square value, we know immediately without this, because obviously this value won't be in the hundreds. And so you get this value from the table, from the StatDisk, from Excel, that it's that, and then obviously this is greater than that, so we reject. And that means they change their mind. That means they add to the TV works, the TV broadcast works. Okay, they don't want the. They may not want the marijuana to, let me see, discrimination for legalization. I think 35 is against. It's just law, fine or imprisonment. Oh, not sure what exactly these means. Do they increase the people who support legalization? This is not very clear. It should, if the TV is broadcast on the EO effects, then this should go down. But after the series was shown, more people wanted it to be legalized. Not very intuitive. Yeah. Anyway, this is for you to apply this goodness of fit test in a real world scenario for count data. As you can see, the percentage, although it's a decimal, although it's like look like a continuous variable, but actually it's a count data. You count how many out of 500 people voted for different options. Okay. Another example, count data again, and you up phase frequency die 60 times, row 60 times, and the phase value were recorded. Okay. All right, so we want to see if this is a fair die, and a fair die should have 1/6 probability, but then let's see if so expected value should be 10 out of 60 for each, so that's 60, 10, 10, 10, 10, 10, 10. And but then observe is like that. So let's do the differences, and you can find oh, it's 6. Yeah, 6. All right, and this compared with the 11.07, so it's less. So they are not significantly different from each. I mean, yeah, we cannot say they are different. So this seems to be a fair coin. Okay. Let me see, contingency table. All right. So for contingency table, now instead of two groups, we have a table. All right. And then here's a scenario. The factors are independent. So previously there seems to be there's only one factor, or you can say but here we have two factors. Okay, two factors. So are two factors independent, or are two factors dependent? Then here's the formula. In principle, rationale wise is the same. Okay. Let's see an example. So in this table, we have religious affiliation, and we have marital status. Okay. So we want to see if religious affiliation and marital status are related, or are they independent? Doesn't matter you're single, you are married, or that won't affect your religious affiliation. If you are single, you need religion more, or if you are not single, you don't need you need religion more. We don't know. So they are in our. I don't know if a master's degree need the right dissertation or not, but in case you need, then you can use this method to test for your hypothesis. You may not sure if two factors are affecting each other, but then you can use it to test for the hypothesis. Okay, so so you have table like that, and you plug in the formula. You will see that okay. So you will calculate E11, E12, E13. What's E11? E11, that means 1 and 1 in this 1, 1, 1, 2, 1, 3, 1, 4. 1, 1 is 1, 1, 6. Okay. 1, 1 is here, and then 2, 1, 1. So that's the sum of each row of the first row, the sum of first column, and then the product of the two and divided by 500. Okay, divided by 500. Okay, let me see. Yeah. All right, and so you do that for all the to find all the E. They are 2 by 5 E values. Okay, and observed value, of course, are in that intersection. Okay. In other words, why we do this is, look, if you divide 116 by 500, you get the you actually get the expected distribution, okay, based on marital status. Okay, 116 over 500, 384 by 500, you get the distribution for marital status. Then you multiply that by 211, then you get expected value for them respectively. This is why, or what each number, this formula means. You see 116 divided by 50, that's a ratio of percentage of marital status, single. And then you multiply that by 211 to distribute that into each category. So if this is the same throughout these religious affiliation, because 116 divided and then 384 divided by 500, you get the percentage which is throughout the religious affiliation. So religious affiliation, if then the test comes out the same, then we can say, oh, religious relation doesn't change the proportion of their marital status. Okay. Otherwise, there should be a significant difference. That's so here you can see the rationale. Or the other way around, you divide this by 500 and you get the ratio. Okay, and then you multiply that by 384, right? And then or 116. You can say that this ratio doesn't change from white with spouse to single. It doesn't change, or it change depending on if they are equal. Goodness of fit. Okay, so so you do that, and then you can say something did not fall in the rejection region, so do not reject. So they are independent. They are independent. Okay, marital status, single or not, they don't change their religious distribution. Okay, so this is section 7.2. We want to go faster. And so you can use the chi-square test and then to compare your result if you do it manually, or you can just use R. I am not against you just using R alone, okay? But then doing manually may double check. Okay, I suggest that you do this the question first, and then you get a hang of using R for the test, and then you can go directly to apply it to a question without doing it manually. Okay. Okay, now for Kolmogorov test. For this one, I will, let me see. Excuse me. For this one, I will just use this file, which you can download from in here. Well, which you can download here in module 1. You can see it right here. No, oh, wait a minute. module 1 right here. Okay, download it from here, and then we read the page 2 to 14 only. I now cover them right now. Okay, so here you have the, I use the, thanks to this gentleman, okay, I use his material. All right, now here's an example. Suppose you have 100 observations. Then you want to see, do they come from n equals 0 and 1? I mean, mean 0 and standard deviation 1, so this is standard normal distribution. So my homework for you is that you generate 100 numbers from exponential distribution function. Obviously, then you will only get positive numbers, and the answer may be obvious, but I do that purposely so you can see, oh, okay, they will be different. Okay, and that you can tell the answer easily, but then you need to do it to Kolmogorov-Smirnov test to prove it. Okay, so this is the hypothesis, the way you write hypothesis, and of course replace that by P by do the samples come from standard normal distribution, or replace the P by standard normal distribution in this case. And of course, this is the rationale they. So you find a cumulative probability. These are the 100 n to n. Assume n is 100. Remember the date 100 observations. So first you rank them. You rank all the numbers from smallest to largest, and then take. Then you can what? And you can find the cumulative probabilities. Obviously, the first one is 1 over 100%, the second one is 2, and so forth. And you have 100 different numbers, so each one has a relative standing in this group. Okay, and that's then, and together is the distribution. All right, but here's the theoretical distribution, expected distribution that we want to compare with, which is from Z. So you, this is, okay. So actually, if you plug those 1 0.01 here and 2 0.02 and so forth, and then you turn those into a Z value, then you can create these values. You just revert the probability to values. I think you can do that with the materials we learned in previous quarter. Then we find the absolute differences. Okay, okay. You compare these 1 by 1 with this. So the first one, this one with what? 0.000. And 0.02 with this one, and 0.03 with this one, and so forth. So you find the absolute value and take the sum of these values and see what the result will be. And so here is the red one is experiential, which is the Z distribution, standard normal distribution. But the green one, the black one, black color curve, you see this here, that is the from the data. But then you see the green vertical line, those are the errors, the differences, deviations from each other. And then you take the square and calculate it in terms of D. And so intuitively, you can tell that look, they are not deviating too much. Otherwise, it would go like here, and they could fluctuate more. So these two distributions, in terms of their cumulative probability, of course, they are. Well, I'm not showing you their PDF function. Yeah, we are just comparing their cumulative probability distribution, and you can see they are very close already. And so the D value test as a critical value can be calculated by dividing 1.36 by square root of n, which is 100. So if that is too small, smaller than that, then we do not reject the null hypothesis. Okay, and then you can see that's the case. And also, if you look at this curve, I can also explain the DD plot or normality plot, because in normality plot, which is a question in another assignment question, in that normality plot, you will say, oh, okay, if they all the points that fall on the same line, then normality assumption is not violated. And this happened to the red line. It happened to be a normal distribution. So it's a perfect example to illustrate a QQ plot or normality plot as well, regarding why it can test whether something is come from a normal distribution. Some sample is drawn from a normally distributed population or not, because you can see here that they are falling almost, all right, almost on the same straight line. You see, like a straight line, right? So you can say that the normality assumption is not violated. Okay, so yeah, good up to here. All right. So, and the rest of it, you can read it. It's up to you. Okay, it's a 2 samples and similar principle, only up to 13. You can ignore the rest of it. Okay, so the last homework question on the assignment 1 is to do the same thing from page 1 to 2 to 10, and by replacing the data set with one that's from exponential distribution with the mean equal to 1. You should be able to generate it from R or Excel, then compare it, do the similarly. I think you should be able to find the answer easy. Okay. Okay, I think this is a good point to stop. Let me see. Okay. Oh, what? Oh, let me see. Are we still there? Let me.
Yeah, I'm still here.
Oh, sorry. I was looking at the Zoom sign. I thought it was cut. I was cut off. But okay, we are good. Okay, good. Any questions so far? So good.
No, not yet. When I grind through the homework problems, so if I have any, I'll let you know.
Okay. Very good. Okay. Yeah. It's not a very challenging. Of course, to understand the question, examples first will help us help the material sink in.
Yeah, definitely.
Okay. Very good. Okay. I think
thanks.
it's a good point to stop, and I will. Let's continue. Next time, maybe on Monday as well, because I have trip all week. Okay. All right. Good. Okay. Great. Have a great day. All right. See you next time.
Goodbye.
All right.